Welcome to WikiPodcast. Imagine a place in the universe so extreme, so unfathomably dense that not even light can escape its grasp. A place where our most fundamental laws of physics seem to just buckle and break under the sheer force of reality itself. Today we're taking a deep dive into these cosmic enigmas, black holes. We're going to explore how they work, what happens inside, and, well, why they're forcing us to rethink reality. So let's start with the basics. When we talk about a black hole, what exactly are we defining? I mean, at its core, it's this astonishingly massive, incredibly compact object in space, right? Its gravitational pull is just so overwhelming that absolute nothing, not even light, can escape its grip once it gets too close. You can kind of think of it like an ideal black body, yeah. Something that absorbs all incoming light and reflects none.
That's precisely it. And what's truly remarkable is that the idea, the very concept of these objects, it sprang directly from Albert Einstein's theory of general relativity.
Yeah.
When you squeeze a mass down to an incredibly tiny volume, his equations basically showed that it would naturally form a black hole. And the crucial boundary around it, that, cosmic threshold of no return, is what we call the event horizon. Once you cross that line, the escape velocity exceeds the speed of light. So you're trapped. Now, classical relativity says they're perfectly black, but quantum field theory, well, it hints at something more subtle. It predicts black holes actually emit a faint thermal glow, often called Hawking radiation. But for the black holes we usually talk about, the ones formed from stars, this radiation is so unbelievably tiny, so cold, it's basically impossible to observe directly.
Right.
Not with our current tech, anyway.
Okay, let's unpack this a bit more then, because this isn't just some cutting-edge idea that popped up recently, is it? The concept of these dark stars, it actually has a surprisingly long history, right? Predating Einstein by centuries.
You've hit on a key point there. Yeah, the fundamental notion goes way back, all the way to the 18th century, actually. You had brilliant minds like Jean Michel and Pierre-Simon Laplace pondering these dark stars objects so incredibly massive, their gravity would make the escape velocity greater than light speed. Michel especially, he had incredible foresight. He even suggested we could detect them indirectly, by their gravitational effects on nearby stars. But here's where it got tricky. When light came to be understood more as a wave, well, the enthusiasm for dark stars kind of cooled off. It just wasn't clear how gravity, as they understood it then, could affect light waves.
Right, and that's exactly where Einstein steps in with general relativity and completely changes the game, isn't it? Like the missing piece finally clicking into place.
Precisely. Einstein's theory, back in 1915, it definitively showed that gravity does influence light's path. And just months later, Carl Schwarzschild found the first exact solution to Einstein's equations. This solution described the gravity of a spherical mass and showed this really peculiar behavior at what we now call the Schwarzschild radius. For decades, physicists sort of wrestled with what this surface really meant. It wasn't until David Finkelstein in 1958 explicitly interpreted it as a boundary you couldn't escape from. Then, the mid-60s to mid-70s, that became the golden age of black hole research. During that time, more solutions were found, like for rotating black holes, and all this intense study led to the profound no-hair theorem.
The no-hair theorem. Okay, that sounds intriguing. What does that tell us about black holes?
It's one of the most surprising things, really. Imagine a really complex, maybe messy star collapsing. The no-hair theorem basically says that once the black hole settles down, it becomes incredibly simple. It loses all its hair, meaning all the unique details of whatever made it are just gone. A settled black hole is completely described by just three things: its mass, its electric charge, and how fast it spins its angular momentum. That's it. Astonishing simplicity for something so powerful.
Wow. So these cosmic monsters boil down to just three numbers. Incredible. And speaking of the name black hole, that term itself has a pretty interesting backstory, doesn't it?
It absolutely does. The phrase black hole was really popularized by the physicist John Wheeler around late 1967. He liked it because it was vivid, had, as he said, advertising value.
Right.
But the term had actually popped up in print earlier, 63 and 64. Science writer Marcia Bartusiak tracked its likely origin to physicist Robert Dicke. Apparently, Dicke compared the phenomenon to the notorious historical prison, the Black Hole of Calcutta, a place people went in but never came out. A grim comparison, but kind of fitting.
Grim, but yeah, fitting. Okay, so let's jump forward. Imagine you're watching something, maybe a spaceship, fall into one of these things from way out, safely distant. What would you actually see? Because of this thing called gravitational time dilation, that spaceship would seem to slow right down as it gets near the event horizon, wouldn't it? It'd look like it takes forever, like infinite time to actually reach it.
Right.
It would get dimmer and redder. That's gravitational redshift, right?
Right.
Until it just fades away, frozen at the edge.
That's exactly right, from the distant observer's view. But now, imagine you're an indestructible astronaut actually falling in, your experience. totally different. As you cross the event horizon, you wouldn't notice anything special. No jolt, no time slowing down from your perspective. Your watch ticks normally. You cross that boundary in a finite amount of your time. According to Einstein's equivalence principle, locally, you, the person falling in, you can't even tell where the event horizon is. It's really mind-bending how relativity allows these two viewpoints.
That's astonishing. So from my view, you're frozen, but you just sail right through. Wild. But okay, then what's at the very center? Where does all that collapsed mass actually go? The singularity.
Ah, the singularity, yes. At the heart of a non-rotating black hole, general relativity predicts this gravitational singularity, a region of, well, infinite space-time curvature and infinite density. All the black hole's mass crushed into a single zero volume point. For a rotating black hole, it's slightly different. It's smeared out into a ring shape. But what's really fascinating and honestly deeply problematic for physicists is that these singularities, they signal the breakdown of general relativity itself. Our theory just stops making sense there. This is where we expect quantum effects must take over because the density is just unbelievably high. And even before you reach it, if you were falling in feet first, the intense tidal forces would stretch you out like spaghetti. It's a process colorfully, maybe morbidly, called spaghettification.
Spaghettification.
Yeah.
Right, not exactly a pleasant ending. And okay, if our current physics breaks down at the singularity, that begs the big question, what happens then? Are there theories about, like, an other side?
Well, for charged or rotating black holes, some theoretical mathematical solutions do hint at possibilities. Things like exiting into a different space-time, basically acting like a wormhole, or even creating closed time-like curves, which would theoretically allow travel into the past. But, and this is a big but, these are generally considered unphysical. They probably wouldn't survive a proper quantum gravity treatment. They're more like mathematical quirks right now. But around rotating black holes, there are other fascinating real regions. There's the photon sphere, this precise distance where light particles, photons, can actually orbit the black hole. It's unstable, but they can orbit. And then for rotating ones, there's the ergosphere. This is a region outside the event horizon where space-time itself gets dragged around by the black hole spin. It's called frame dragging. In the ergosphere, you literally can't stand still relative to distant stars. You're forced to rotate with the black hole. And this region allows for something called the Penrose process, a way you could, surprisingly, extract rotational energy from the black hole.
Extract energy from it. Okay,
Yeah.
that's counterintuitive. So where do these incredible objects even come from in the first place? They don't just pop into existence, surely.
No, they don't. The main way we think the black holes we see are formed is through gravitational collapse. This happens when really massive stars, much bigger than our sun, run out of nuclear fuel. Their internal pressure just can't hold up against their own immense gravity anymore.
And if that star's core is heavy enough after the explosion, there's just no stopping it, is there? It just keeps collapsing inwards. What's that critical point?
Exactly. If the leftover core, the remnant, exceeds a certain limit, it's called the Tolman-Oppenheimer-Volkoff limit, roughly 3 to 4 times the sun's mass, then even the pressure that supports neutron stars isn't enough. At that point, collapse is inevitable. It crushes down into, well, effectively infinite density, a black hole. And we classify them by mass. You have stellar mass black holes from these stars, and you have supermassive black holes, millions to billions of solar masses lurking in galaxy centers. And maybe, hypothetically, primordial black holes formed way back in the early universe.
Right. And once they're formed, they don't just sit there quietly. They can actually grow.
Right.
Right. By gobbling up stuff around them.
Yeah.
Cosmic cannibalism, almost.
That's a great way to think about it, yeah. Black holes definitely grow. They pull in surrounding gas and interstellar dust that's called accretion. This process is thought to be super important for how those supermassive ones got so big. They can also grow by merging with other stars, or even colliding and merging with other black holes. That cosmic cannibalism really is how the biggest ones likely achieve their enormous sizes.
Okay, this leads to a really mind-bending question, though.
Mm.
If absolutely nothing, not even light, can escape,
Mm.
how can they ever disappear? Because theoretically, they can, can't they?
Yeah.
Which seems to contradict everything.
It does seem contradictory, doesn't it? This is one of the most amazing theoretical predictions coming from Stephen Hawking back in 1974. He proposed Hawking radiation. The idea is, counterintuitively, black holes aren't perfectly black. Because of quantum effects near the event horizon and weird quantum fluctuations, they emit a very faint thermal radiation. This means they actually slowly lose mass. They effectively evaporate over absolutely enormous timescales. And what's even stranger is the relationship between mass and temperature. Bigger black holes are actually colder and radiate less, so they evaporate much, much more slowly.
So black holes aren't truly black after all. That completely flips the script. But when you say slowly, how slow are we talking here? What kind of time scale is needed for one to just evaporate away?
We're talking timescales that are just almost impossible to really wrap your head around. A black hole with the mass of our sun, for instance, would take something like 10 to the power of 64 years to completely evaporate. That's a pion followed by 64 zeros. For the supermassive ones, like in our galaxy center, it could be up to 10 to the power of 106 years. 106 zeros. So yeah, while evaporation is theoretically real, it plays out over cosmic timescales far, far longer than the current age of the universe. They aren't disappearing anytime soon.
Right, okay. Mind-boggling numbers. So if they're invisible themselves, how do we actually know any of this is real? It sounds like astronomers are chasing ghosts. They must rely on seeing the effects, right? Their gravity influencing things around them.
You've nailed it. That's absolutely key. Indirect evidence is crucial. But recently, we've gotten even more direct proof. One of the most striking examples is from interferometry. The Event Horizon Telescope, the EHT, managed to capture those first amazing images. First, of the supermassive black hole in galaxy M87 in 2019, and then Sagittarius A, our own galaxy's central black hole, in 2022. Now, it's important to be clear. We're not seeing the black hole itself. That's still black. What the image shows is the superheated gas swirling right at the edge of the event horizon, its light bent and distorted by the intense gravitational lensing. And often that ring of light looks brighter on one side. That's due to Doppler beaming gas moving towards us at relativistic speeds. It gets brightened, giving us this sort of lopsided view of the black hole shadow.
So we can kind of see their silhouette against the glowing gas. Incredible.
Yeah.
But the universe gave us an even more direct confirmation, didn't it? We literally heard them colliding through ripples in space-time itself.
Indeed. That was a monumental moment. In 2015, the LIGO Observatory made the first ever direct detection of gravitational waves. These weren't light waves, but ripples in the fabric of space-time itself. The signal came from the cataclysmic merger of two black holes, one about 36 times the sun's mass, the other about 29. This was huge because the detected signal perfectly matched the predictions from Einstein's general relativity for such an event. And crucially, the final part of the signal, the ring down, as the newly formed single black hole settled, confirmed the presence of a photon sphere, something only expected around objects as compact as black holes. It was like hearing the universe confirm Einstein was right.
And we have solid proof of one right here in our own cosmic backyard, don't we? At the center of the Milky Way. Like really solid evidence.
Absolutely. Sagittarius A. Since the mid-90s, astronomers have been painstakingly tracking the orbits of stars whipping around this unseen object right at the galactic center. By watching these stars, especially one called S2, which has completed a full orbit, they've calculated that there must be an object with about 4.3 million times the mass of our sun packed into an incredibly small space. There's just no other known astronomical object that could pack so much invisible mass into such a tiny volume. The evidence for it being a supermassive black hole is overwhelming.
Okay. And beyond seeing shadows and hearing waves and tracking stars, there's another big way they give themselves away, isn't there? It's about how they feed.
That's exactly right. Accretion. This is how black holes become visible across vast distances. As gas gets pulled towards a black hole, it usually doesn't fall straight in because it has some rotation. Instead, it forms this swirling, flattened structure called an accretion disk. Friction within the inner parts of this disk heats the gas up to millions, even billions of degrees. This superheated gas then shines incredibly brightly, emitting huge amounts of radiation, especially X-rays. This is what powers things like quasars, those intensely luminous cores of distant galaxies, and X-ray binaries, where a black hole is stripping gas off a nearby companion star. These bright accretion processes are like signposts saying, black hole here.
Right. So even though we can't see the hole, we see the fireworks display around it. But despite all these incredible discoveries, black holes still present these deep, fundamental mysteries, don't they?
Yeah.
Places where our physics just seems to hit a wall.
Definitely. And perhaps the most famous, most debated one is the black hole information loss paradox. It's a real head-scratcher. Here's the conflict. General relativity, as we discussed with the no-hair theorem, suggests that almost all the detailed information about whatever falls into a black hole is just lost forever. Only mass, charge, spin remain. But quantum mechanics, our other bedrock theory, has a fundamental principle called unitarity, which basically insists that information can never be truly destroyed. It can be scrambled, transformed, but it's always theoretically recoverable. Hawking radiation, as we currently understand it, doesn't seem to carry that detailed information back out. So where does it go? It looks like it's just gone. Violating quantum mechanics, it pits our two best theories against each other.
So it's like you said, throwing a book into a cosmic shredder, but then the shredder itself vanishes, leaving absolutely no trace of the book's contents, not even in principle. And quantum mechanics says that just can't happen. This sounds like a major crisis for physics.
It really is a profound crisis, and it forces us to ask this really important question. To resolve this paradox, which fundamental idea has to give? Is it something in Einstein's theory, like the equivalence principle? Is it unitarity in quantum mechanics? Or maybe our understanding of local quantum field theory? We don't know the answer. And things got even more complicated recently with the firewall paradox. This came out of attempts to solve the information paradox, but it suggests that trying to save both relativity and quantum mechanics leads to other inconsistencies, possibly involving a breakdown of space-time smoothness right at the event horizon itself, a fiery wall. It just deepens the mystery.
And I know there are some pretty wild theoretical alternatives out there trying to sidestep these paradoxes, right? Things that look like black holes from the outside, but are fundamentally different on the inside, like fuzzballs or stars.
Precisely. Theories like the fuzzball model from string theory suggest there might not even be a singularity or a sharp event horizon. Instead, the black hole might be a dense, stringy object. Other ideas propose different kinds of exotic compact objects. These are all attempts to build a theory of quantum gravity, something that can unite general relativity and quantum mechanics. Black holes are the ultimate testing ground for these ideas. They really represent the edge of our knowledge, the place where gravity and quantum mechanics collide most dramatically. Understanding them is key to finding that next, deeper theory of reality.
Thanks for listening. Write us your opinion on it. What do you think is the most mind-bending paradox about black holes? Or which fundamental law of physics do you think will ultimately need to change to fully understand them? Let us know in the comments. Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.